purpose of this video is to look at how we can interpret the output when we run a JAGS program. And so you recall we created this object results by using the runjags function, keyword model. This was the name of the model. All these different features here. Open parenthesis here, close parenthesis here, items separated by commas. So we've got this object called results, and then we make a summary of these results using this keyword summary, and we can name it anything. I've called it out. Type in print out. This is what we get, and that's what I want to go over. So what sort of output do we get? Well, we're interested in the parameter theta, the Bernoulli binomial parameter, in a study where we're trying to determine theta, the proportion of the individuals in the population that are right-handed. And so we've got here is the lower and the upper 95% credible interval, sometimes referred to as 95% highest density interval. So you can see here we've got, as an example, not the particular example of handedness, but a general example that shows what HDI means. So 95% of the values of some arbitrary value y lie within this range. By virtue of the fact that this distribution is not symmetrical, the area here is not going to necessarily be the same as the area out here. We've got the values of the median, the mean, and the mode, and they're just the typical values that you would associate or you would have learned about in your introductory statistics courses. What else do we have? We've got the standard deviation. So recall we would have had 30,000 estimates of theta because we had 3 chains with 10,000 observations each. The standard deviation of all those values of theta is 0.074. Now, before moving on to the rest of this table, I want to come down here and think some more about this notion of autocorrelation. And I want to point out that this particular figure here is not. It is definitely not for the handedness study. It's for another study that we're going to see in week 9 involving batting. But what we have here on this axis, the vertical axis, is autocorrelation. And what we have on the horizontal axis is the lag period. And as we saw earlier, as the lag period increases, the amount of autocorrelation tends to go down. And what I want to think about now is this ESS, which Christie sometimes represents as effective sample size. How is that calculated? Well, in the numerator, we have n. And what is n? N is the number of observations, and n is going to be 30,000. Because we've got 10,000 observations in each of 3 chains. And then we got this number 1, and then we've got this thing. So what this thing is doing is it's multiplying the number 2 by this bit here, and this bit here is just the sum. Sum up all these values here. So you sum up all the values of autocorrelation over all the autocorrelation lags, take n, divide it by that, and that gives the effective sample size. Now again, to stress, this figure here is not for the handedness study. In fact, what happens with the handedness study is that the data are so simple that under some circumstances, the autocorrelation might actually be negative. And if the autocorrelation factor is actually negative, then this number here, once you take 1 and subtract a small negative number from it, this number here can actually be greater than with 30,000. That's kind of an anomalous situation, unique to a very simple study, the handedness study, and not something that you're likely ever to see in practice. So, now with that, let's go back up here. AC2 means that I've asked for autocorrelation with a lag of 2. So again, this is not the handedness study, but that would be a lag of 2. SSEF. SSEF is actually greater than 30,000 because in the handedness study, because it was so simple, there was a negative autocorrelation. And so we actually have an effective sample size that's greater than 30,000, but that's going to be a very rare thing indeed. Here we have the standard error of the observations. Now, you think in regular statistics, you take S to get the standard error and divide it by square root of n. What we're going to do to get this is that we're going to take effectively S, the standard deviation, and instead of dividing it by the square root of n, we're going to divide it by the square root of the effective sample size. This thing here is the standard error, or excuse me, this thing divided by the standard deviation. So we take this MCERR as a percent of standard deviation, and that's equal to 0.6. This thing is described in your notes, and I'll talk about it a little bit in a moment, but this just is an indicator of how well the chains have mixed. So it's a reflection of the mixing of the chains. And the recommendation is that this value should be less than 1.1, and in this case it is, so everything is cool. So that's what you get when you print the results. So get a summary results, then print it. You get what we just saw. If you do plots of results, you get this. And here we have the chains. And we have 3 of them, and they're in different colors. They're the iterations, and you can see that the chains are nicely mixed. And as a consequence of this nicely mixed chains, that's why we have this very good value up here, which is a 1.0, which shows that you've really got complete mixing of those chains. Here we've got really what we want. So this is theta. And this is, ta-da, posterior distribution of theta. So this is what we're all about. This is our goal really, is to get this sort of thing. This is the posterior distribution of theta. If you look at the posterior distribution of theta, you can see that it's got a mode around 0.8. And if you come up here, it's always good to check the results. You can see that the median was 0.79, the mean was 0.783, and the mode was 0.802, so that's cool. What we have in C is, if B is the posterior distribution, then C is just, maybe let's call it accumulation, is the accumulation of the probability distribution. So in other words, we just start here, and we just start adding up these values, and you get something like this, which obviously at the end is going to add up to 1.0, because this is a good, this thing down here is a good probability distribution. So the area under the curve is 1.0. So as you move in this direction, adding up these values, you get this nice sigmoidal curve that eventually winds up at 1.0. And this is the autocorrelation plot. So, as I said, When I tried to describe what autocorrelation was, I used the example from week 9. I didn't use the example from the handedness study because this is the autocorrelation plot from the handedness study. And you can see just by virtue of the fact that it was such a simple study, essentially there is no autocorrelation. You do get an autocorrelation of 1 at a lag of 0, but of course that isn't terribly meaningful. So bottom line is, these are the sorts of things you can do to look at the results either by plotting or by printing the output.